This is it. So this is on your screen right now. This is our very first Physics 212 problem. This is from chapter 18. The title of chapter 18 is heat. Yes, basically heat. And ideally, and again, it's okay if it's not happening today, but ideally you would have watched the lecture video that I posted on YouTube and watched it once or twice, pause, rewind, replay, fast forward, slow down. And then also ideally, and in keeping with that sort of, in the same thread as watching the lecture video, you've really started to fill out your green sheets. And the green sheets are golden because you can use your green sheets on exam, use these on your exam. So you have an incentive to fill out those green sheets as meticulously as possible because you get to use your green sheets on exams. So that's why, again, you might really want to fill them out completely and accurately. And you might want to supplement them with additional notes as well. So those are yours to use during the exam, but you can only use green sheets that come from me directly and in your own handwriting, meaning you can't photocopy green sheets from someone else, and you can't bring extra resources in. It's just the green sheets on green colored paper, hence the name green sheets, that you get directly from me and filled out directly in your own handwriting. And the thinking there, which I totally like this thinking, when you write something down, when you write lecture notes down, it's typically pretty helpful. I mean, I was the type of student who would take notes during class, and then I would recopy my notes to make them neater. And just the act of recopying the notes themselves was actually pretty darn helpful, because as you're writing stuff down, you're hopefully thinking about what you're writing down. And again, I'll talk a lot about that type of strategy and tactics on Wednesday, but for now anyway, but I will go off on tangents like this. We're in our first Wiley Plus quiz. This is chapter 18, quiz number 1. And let's solve it. So chapter 18, quiz number 1. And again, this is actually a homework problem. So not only are you going to get credit on the quiz, you're basically going to know how to solve the homework problem. And some of you might be thinking, what a great class. The instructor is doing everything. The instructor is basically solving the quizzes for me, and the instructor is solving my homework for me. What could be better? That might not be what you think it is. I'm doing what I'm doing just to make sure you completely have a foundation. But your work, the amount of time I'm going to spend solving these problems should be dwarfed by the amount of time you spend solving these problems, because you're going to solve these problems and then you're going to solve a whole bunch of practice problems. And that's going to take a lot of time on your part, because it's practice makes perfect. Practice is like the secret sauce of this class, and obviously of most classes. But the more you practice solving problems, and then the more you test yourself solving brand new problems, the more ready you're going to be for the exam. So, all right. Point, and everyone has different numbers. So you're looking at a problem that has some number that's probably different than 0.496. So we all have the same problem, but we all have different numbers. So just know that. In my case, I have a 0.496 sample of something placed in a cooling apparatus that removes energy as heat at a constant rate. So one of the key things here is to read the problem statement very carefully and repetitively, and then start providing a visual. Every exam solution needs you to cough up a supporting visual. So I come from a deep engineering background, and I'm used to creating a whole bunch of engineering design documents and a whole lot of proposals and a whole lot of requests for information. So I definitely have a lot of experience with documentation, and I kind of run these classes the same way. You need to have very easy to follow documentation with supporting commentary, explanatory comments. So I'm just going to draw what I read, basically draw what you read, make it very obvious what's going on. So I'm going to draw this little container here. Here's a container, and this is actually going to be very similar in some ways to what you're going to do on Thursday during our first lab. Okay, so there's my container. So this is my container, and then I have an object, and maybe I'll just say, well, here's my object, just a chunk of copper, for example. So there's my object sitting in this cooling apparatus, and in this cooling apparatus, there's a device. A sample is placed in the cooling apparatus that removes energy as heat at a constant rate. Okay, so I'm going to indicate that as follows. Heat is leaving this object at a constant rate. So and again, you guys spend an enormous amount of time doing what I'm doing. Read the question super carefully, super repetitively. My mass here, this is M equals 0.496 kg. It's placed in a cooling apparatus that removes energy as heat at a constant rate. So you know what? We can say something about that. Heat is being removed at a constant rate. Q stands for heat. So let me go off on a bit of a tangent here. What forms of energy have you formally been introduced to thus far in your academic career? And I can think of translational kinetic energy. I can think of rotational kinetic energy. I can think of gravitational potential energy, elastic potential energy. Am I leaving anything else? Is there anything else that you guys have? There's lots more forms of energy. I'm just thinking, what have we formally been exposed to right now? Maybe that's it. If I'm forgetting something, unmute your mic. Again, I'm going to let you guys chat amongst yourselves in the chat box, and I will respond to unmuted microphone comments and questions. So anyway, we're going to add to this list. We're going to add a letter called Q. And Q stands for heat energy. So this is another kind of energy that goes to the list of energy items. And there's more. There is magnetic potential energy. There's electrostatic potential energy and more. But there's one thing that's very notable about this addition. So heat energy, which is introduced formally right now, stands in a different category compared to all of these forms of energy. These forms of energy, kinetic energy, potential energy, these are considered ordered, meaning they're kind of well behaved, meaning that you can manage them. They're manageable. Like if I want to lift up, if I want to lift a block of sand or a bag of sand from the floor to a tabletop, I can do work, and I can use gravitational potential energy and convert gravitational potential energy into kinetic energy. And you guys should be familiar with that. These these energy transformations. You should have seen something like this, that whatever kinetic energy I start off at state A plus whatever potential energy I have at state A plus whatever non-conservative work happens, well, that is the same as the sum of the kinetic energy at state B and the the potential energy at state B. So this is basically a common expression I use for conservation of energy. This is conservation of energy. And in this case, the energy that's being conserved is basically kinetic energy and potential energy. So conservation of energy. So energy can change forms, but you can't destroy energy. And you can push back and say, yeah, Chris, you can destroy energy and through nuclear reactions. So yeah, with that caveat, outside of nuclear processes, energy can change form, but you can't destroy it, which is kind of cool because all you have to do is keep track of it. All right, so these are ordered energies. Kinetic energy and potential energy are ordered types of energy, and which means they're manageable. You can kind of make them do what you want by managing them through clever engineering scientific processes. This is disordered energy, meaning random. And so just think, when you think of heat energy, you're thinking of randomness, chaos, entropy, disordered, mixed up. So that's a key difference. That this is a difference worth stressing right now. The difference between ordered energy and disordered energy, and basically how that manifests itself is that it's typically heat is a lot harder to manage versus the more simpler ordered energy types. So again, just think of randomness, chaos, mixed up, violent, et cetera, et cetera. All right. So anyway, this is what I'm referring to when I'm saying I'll go off on these deep tangents every now and then, which is consistent with the lecture video. All right. So energy is being removed at a constant rate. So I'm still kind of focused on that first sentence. Q is being removed at a constant rate. So other than just saying, okay, constant rate, that word rate kind of nudges me to think of power, because power, P for power. What is power? Power is the rate. Power is the rate of doing work, or it's the rate of consuming or producing energy. All right, so that's why I'm thinking of power. Power is the rate of doing work. So in this case, we could say, well, power is the rate of heat removal. So I'm going to key on that and maybe just keep that around for future consideration. But that's why I'm thinking of power considerations, because this word right here, rate, in physics and engineering, rates are typically a special word. This figure, so now we have a graph. We have a graph of temperature versus time. This figure gives a temperature T of the sample versus time. The horizontal scale is set so we have a scaling factor. T sub S, for me, it's 120 minutes. Maybe for you, it's something different. The sample freezes during the energy removal. The specific heat of the sample in its initial liquid phase is 3,004 joules per kilogram Kelvin. What's the sample's heat of fusion? What's the specific heat in the frozen phase? All right, so let's start. Let's actually start getting to the nitty gritty. All right, I guess the first thing I'm thinking, just because this is my engineering mindset, I'm thinking I'm going to consider this to be like segment A, and this is segment B and segment C. I mean, this seems to be clearly a 3-segment process. All right, and I'm just, as long as I'm here, I'm going to say, well, A represents cooling. So A represents a cooling liquid. And I just want to make sure, is this liquid? It says the sample freezes during the energy removal. Okay, so I know one thing. I'm starting off with a liquid. How do I know I'm starting off a liquid? Because it freezes during this whole process. Segment B is phase change. This is a phase change process. And specifically, I'm phase changing from liquid to solid. And whenever you have a phase change from liquid to solid, that's called freezing. There's sublimation, there's freezing, there's boiling. Right, so I'm going through a phase change. So I actually have a mixture. During segment B, which is the freezing phase, I actually have a mixture of liquid and solid. They both coexist. And that's noteworthy, because all of the energy that's being removed is not changing the temperature. Because if you notice, this is a flatline region. So this flatline region during segment B means the temperature is not changing, but yet I'm continuing to remove heat. I'm continuing to remove heat at a constant rate because of this. I have some kind of device that's removing heat at a constant rate. So if heat's being removed and my temperature remains constant, that's because I'm undergoing a phase change. I'm flatlining. All right, so segment C is a cooling solid. So I've turned to ice. My object has turned to ice, and it's continuing to get colder, cooling solid. All right, so that's helpful. For me, that's helpful. For me, it's helpful just to really get the big picture set up. You should think about doing this on the exam because I think all of this conversation is going to make solving the actual problem, I think, easier. So we know that with all of that in mind, part A says, what is the sample's heat of fusion? So for part A is asking this: what is the sample's heat of fusion? So you know what that's looking for? That's looking for L subscript F. So L subscript F is what we're looking for in part A. L subscript F stands for latent heat of fusion. I can write that down. Latent heat of fusion, which is a material property. This basically depends on what you're dealing with. The latent heat of fusion for water is different than for cork, and it's different for hydrogen. So every material has its own specific latent heat of fusion. Again, it's a material property. Latent heat of fusion. Latent heat of fusion refers to what's going on when you go from liquid to solid or from solid to liquid. That's why I'm doing a double-sided arrow, a back and forth arrow. Latent heat of fusion is the amount of energy required to turn a substance, an object or a substance, from liquid to solid or from solid to liquid. And it's you would be given this information. You don't have to memorize it. So that's our dollar sign. Dollar sign means I need to find that variable. So how do we do that? I'm thinking, I know that Q equals ML subscript F. And you know that too. And you're thinking, well, I don't know that. This is the first time I've seen Q equals M times L subscript F. But this is, again, why you would ideally watch the lecture video ahead of the lecture. And today you didn't really have it. Well, you could have done it, but you don't have the green sheet. So I'm going to kind of go into deep dives for this stuff. Normally I would say, okay, well, you guys know from watching the lecture video and filling in your green sheets that Q equals ML subscript F. So just be aware that that's the approach I'm going to take every Tuesday when I do what I'm doing. I will assume that you know what Q equals M times L subscript F is. You know that formula, you know what it means because you've watched the lecture video. So just make sure to keep that in mind. I know Q equals mass times the latent heat of fusion. So let's run with this. So if that's true, then all I have to solve is say, well, let's do some algebra. The latent heat of fusion, therefore, equals Q over M. And I know the mass, so I'm feeling confident. I know the mass of this object. It's given to me. But then this is where I say, uh-oh, how much heat got removed? And I am focusing on segment B. So this is a segment B focus. So maybe I'll add that here because I need to know the latent heat of fusion, which basically corresponds to the phase here, this flatline phase represented by segment B. Refer to segment B. So just a little helpful comment here. Here's segment B. That's what I'm focusing on. So how do I find Q? That right now that's stumping me, but then I'm going to say, aha. I know the rate of heat removal is constant. So look at, and then this is where you go back to the question. The sample freezes during the energy removal. The specific heat of the sample in its initial liquid phase is 3004 joules per kilogram Kelvin. So I'm going to look at segment A. I'm going to look at segment A because they gave me some information about segment A that they didn't give me about any other segment. Segment A, so the specific heat of the sample in its initial liquid phase right here. This is what I'm keying on. Okay, this is known as specific heat capacity. So this is C. This is C equals 3004 joules per kilogram Kelvin. Okay, and C stands for specific heat capacity. So this is a big part of chapter 18. It's a big part of your lab on Thursday. It's a big part of exam 1, specific heat capacity. It's part of thermodynamics, specific heat capacity. And again, I know I'm introducing this to you now, but normally, again, I would start every sentence with the following. Because you've watched the lecture videos and filled in your green sheets, you know what specific heat capacity is. So just trying to really stress that. So how can I take advantage of that? Well, so look at A. During cooling, which is segment A, I know this, Q equals MC delta T, which is another new equation. So right now you've been confronted with two fundamental equations. Q equals M L subscript F. And now here's the second one. Q equals MC delta T. These are brand new, but introduced very thoroughly in the green sheets and the lecture videos. And then you've been exposed to a new term, L subscript F. So there's some new stuff right here. Q equals MC delta T. I basically refer to this as the specific heat capacity equation, which is, again, the heart of Thursday's lab, specific heat capacity equation. Okay. So how can we take it? The only reason I'm doing this is because I'm stuck. I don't know what to do to find L subscript F. So I'm just saying, well, I'm just looking for a lifeline. And I'm thinking segment A might provide a lifeline because I do know a lot of information about segment A. So that's the tree I'm barking up. And you know what? If I run into a dead end, you just bark up another tree. So let's divide by time. So divide by time to get rate, to express as rate. That's my motivation. I want to express this as a rate because, once again, they said heat's being removed at a constant rate. So I'm going to take Q equals MC delta T, and I'm going to divide through by time, which means I'm going to divide the left side by time, and I'm going to divide the right side by time. And why did I do that? Because Q over T, as mentioned, is power, the rate of heat removal. This equals the rate of heat removal, which is a constant. So once I figure this out from part A, segment A, then I can use it for segment B. Okay. So what do I do now? I'm going to look at the graph, and I can see, and this is graphical analysis time here. I can see that for segment A, my temperature started at 310 Kelvin and then cooled to 280 Kelvin. That's what happened during segment A. as far as temperature. Also for segment A, my stopwatch, my clock started at 0 seconds and ticked off to that point right there. So I know a lot. So you know what? I'm just going to keep going with this. All right. So number 7, Q over T, which is power, equals M. The sample, my sample is 0.496. So you would be writing down your sample size, 0.496 kilograms. So there's M. C, they told me my specific heat capacity for this substance while it's in the liquid phase is, for me, they said 3004 joules per kilogram Kelvin. So 3004 joules per kilogram Kelvin. So once again, I have M. Here's M. I got the M. I got the C. Now I just need delta T. So here's delta T. Delta T is final minus initial. I ended up at 280. I started off at 310. So that's my delta T. Here's delta T. I ended up final 280. My initial was 310. Okay, so, and those are Kelvin. Ended up at 280 Kelvin, started off at 310. That looks good to me. And then I just need to divide by time. So I'm going to take this whole statement here, divide by time, because it's MC delta T divided by time. How much time ticked off? And the answer is 4 boxes. So if I look at my graph, how much time did it take to go from 310 Kelvin to 280 Kelvin? And the answer is 4 boxes. Look it up. Here's one box. That's box number 1. This is box number 1, box number 2, box number 3, box number 4. So it took 4 boxes to go from 310 to 280. So maybe this is just my way of doing it. You can do it your way. I basically have 4 boxes. How much time did it take? It took 4 boxes. And now I need to convert from boxes to time. So 4 boxes times, what could I do? Times TS right here. So my value is 120 minutes per 8 boxes. That's my conversion factor. And let me just talk about that. On my screen, this scaling factor, T subscript S, is given. It's saying that value, T subscript S is given, in my case, as 120 minutes. Okay, so 120 minutes comprises 8 boxes. So this is 1, 2, 3, 4, 5, 6, 7, 8. So 120 minutes is the same as 8 boxes. So that's where I'm getting my conversion factor from. So 4 boxes times 120 minutes per 8 boxes. And I need to convert from minutes to seconds times 60 seconds per minute. All right, and then let's calculate that. But before we calculate that, let's cancel units. So let's see here. Kilograms here cancels with kilograms here. Kelvin here cancels with Kelvin there. Boxes cancels with boxes. Minutes cancels with minutes. So I don't know what the number is yet, but I do know I'm going to end up with joules per second, which is good. I can see the only unit that I did not cancel out is joules and seconds. So that makes me feel good. That's dimensional analysis. You guys will always do this on your exams without fail, because I'll say, make sure to include dimensional analysis. So I do get joules per second. And now I just got to, let's get a number. So I have 0.496 times 3004 times 280 minus 310 divided by 4, divided by 120, divided by 60 times 8, and I get some number. Store alpha A, and I'm gonna double check this. I tend to do calculations like multiple times just to double check, but right now I'm getting minus 12.416 and some change joules per second. You'll get a different number. And I'm just going to do it again. 0.496 times 3004 times 280 minus 310 divided by 4 divided by 120 divided by 60 times 8. Okay, I'm getting the same number again. So I'm feeling pretty good about that store. So now I'm going to write down this. Some of you recognize this acronym. I'm going to make sure to store this in my calculator memory. So SICMA. SICMA means store in calculator memory. You don't want to round off. This is an intermediate result. So, I mean, if you're really very much dedicated to sig figs, you don't want to round this off. You don't want to sig fig-ize this number yet. It's just an intermediate number. Store in calculator memory. So that's where this acronym comes from. S stands for store, I stands for in, C stands for calculator, M stands for memory. So I'm going to put it in my memory location just because I think I might need to use this again. All right, so this is a breakthrough. We're not done, but I am feeling pretty good about this because this is the rate. Q, heat, which I'm just writing in Q. Q is removed at this rate, which that negative sign makes sense because that means removed. Q is removed at this rate. And now I can reuse that because whatever that rate is, negative 12.416 or whatever your number is, that's the same rate as for segment B. So I'm going to go over here and cut to the chase. All right, 7, step 8. Step 8, so for segment B, I'm going to once again say, well, all right, L subscript F equals Q over M. So I'm just recycling that expression. This is my dollar sign. This is what I need to find for part A. So let's run with it. The latent heat of fusion is going to equal Q. Q is going to be power times time all over M. And let me just talk about that again. Power is the rate of doing work, the rate of producing energy. Power is basically the rate of energy per time. And in this case, power is the rate of removing heat. So if P equals Q over T, then Q equals power times time. That's where step 10 comes from. So now I really am feeling good about things because I'm going to keep going. L subscript F equals power. And you know what that is? That's power is sitting there in my memory location A. So I'm going to take the contents of memory location A, which is what I solved for in step 7, times time. How much time? How much time did it take this object to fuse from liquid to solid? What was the fusion period? And the answer is 3 boxes in my case. So let me just clear the deck here. Segment B required 3 boxes worth of time. Here's box number 1, box number 2, box number 3. So I have 3 boxes worth of time. So I'm going to just This is my way of doing it. You can do it your own way. You might be thinking right now, I have a better way of doing it, or a way that's better for me. And the answer is you should use your method. But for me, this is how I do it. I'm going to say how much time. Well, I have 3 boxes, and I need to convert from box to time. So 3 boxes times T subscript S times 120 minutes per 8 boxes. That's my conversion factor. And I need to convert from minutes to seconds times 60 seconds per minute. So that is my numerator, because let me just sanity check myself, and feel free to chime in with questions or with corrections. This is power. So I have the power sitting in calculator memory location A, and all of this collectively is the amount of time required to complete segment B. And my denominator is the mass, and that hasn't changed. That's 0.496 kilograms. So if I do cancellations, let's see. My units for A, according to my joules per second. So A is sitting here in joules per second. So this is joules per second. So if I go through and do this cancellation, joules per second, boxes cancels with boxes, minutes cancels with minutes. This was joules per second, so seconds cancels with seconds, and I am left with joules per kilogram. So that's great news, because I expect latent heat diffusion to be written in terms of joules per kilogram. In this case, they want kilojoules, and we can do that conversion factor. So I'm feeling very good about my dimensional analysis, because it is spitting out joules per kilogram. Now it's number time, alpha A times 3 boxes times 120 divided by 8 times 60 divided by 0.496. Okay, so here's what I have. I have L subscript F equals negative 67,590 joules per kilogram. They want the answer in kilojoules, so I'm going to convert to kilojoules. So times my conversion factor, 1 kilojoule per 1,000 joules. So there's a conversion factor. And the other, so then this answer now becomes L subscript F equals negative 67.59 kilojoules per kilogram. And then I'm going to say ignore the negative. So that negative, the purpose of this negative was first appeared right here. This negative sign first kind of came to life, well, right here. And that's basically saying, hey, this power is removing heat. So I'm going to ignore the negative, because I don't care from a latent heat diffusion point of view. This is a constant. So the fact that this device is removing heat or would be adding heat doesn't matter in terms of the constant. So that's why I'm going to say my final answer is the latent heat diffusion is just going to be 67.59 kilojoules per kilogram. And again, I'm ignoring that negative sign. Just basically was almost a sidebar conversation that says, hey, heat's being removed, so we don't need to actually include that in our final calculation. That's the answer to part A. So with a lot of me going off on wild tangents, but these tangents make the difference between just, you guys don't care about getting the right answer. You care about getting the right answer and learning and retaining your mastery, developing mastery and problem solving techniques, because that's what your exams need. So part B says, What's the specific heat in the frozen phase? So we're going to keep going. I'm pretty sure we're going to be able to go through this quite quickly just because of what we've been through now. What is the specific heat in the frozen phase? So continuing with step 15, part B wants, what is C? C, this is, again, C stands for specific heat. C, and I'm going to give it a subscript C. So C subscript C, this is referring to as the specific heat capacity of material in solid state. Because frozen, when this material becomes frozen, it is a solid in solid state. So C subscript C refers to that. This C right here, this is referred to as specific heat capacity. This C right here, this is referring to segment C as labeled on my graph. So let's run with that. Number 16. Well, I know that this for a cooling solid, which is what I have during segment C, the solid is cooling. For a cooling solid, it's Q equals MC delta T. That's what I know. This is the specific heat capacity equation. This is one of the, again, two brand new equations that are thrown at you. So it's not too bad. But for a cooling solid, this is not phase changing, it's cooling. So it's Q equals MC delta T. All right. So I'm going to subscript this. This is C subscript C. So it's very specifically, it's C subscript C because I'm referring to segment C. And I'll do this as well. All right. So let's just algebraically rearrange. Here it is. This is the dollar sign. C subscript C, which is the dollar sign, equals Q all over M delta T. So let's run with that. What's Q? Same thing. Q is going to be power times time all over M delta T. Delta is always final minus initial. So what's my final temperature? On my graph, my final temperature is 260. And my initial temperature was 280. Final minus initial for me is 260 minus 280. And those would be units of Kelvin. Always include the units. Okay, so let me keep going with this. 19. C subscript C. I'm going to run out of space. So let me move some stuff down. I'll get rid of this. SICA means store in calculator memory. We know that now. Okay, so number 19. The specific heat capacity of this material in its solid state is power. And I know that power was stored in calculator memory location A. Basically, steps 1 through 7 spit out this result right here. So power is sitting there in calculator memory location A. How much time ticked off 2 boxes? So here's the time. 2 boxes worth of time, 2 boxes. And I'm looking at here, right? This is 1 box. This is 2 boxes. So 2 boxes of time were required for this object now in the solid state to cool from 280 to 260. So it's 2 boxes, and then I'm going to convert 120 minutes per 8 boxes. I should stuck that in a calculator memory location too. And then I'm going to convert from minutes to seconds. So I have 60 seconds per minute. So everything in this enclosed by these parentheses, this is my time. 2 boxes times 120 per 8 boxes times 60 seconds per minute. And then my denominator is the mass, which is 0.496 kg times my temperature difference, delta T, 260 minus 280 Kelvin. Again, I remember this is joules per second. So I'm going to do the dimensional analysis. Boxes cancels with boxes, minutes cancels with minutes. This second cancels with that second. And then that's it. So I am going to end up from a unit point of view, I'm going to end up with joules per kilogram Kelvin, which is good news. That's what I would hope to end up with, because I know from experience, those are the units for specific heat capacity. Now all I need to do is get the number. So this is step 20. All right. Alpha A. Okay. And I get 2253. C subscript C equals 2253. 2253. That's my answer to part B. I'm done. My dimensions are good. Joules per kilogram Kelvin. My number's good. So that's it. Spent an enormous amount of time just doing one problem, but that's because it's day one. Nobody has watched the lecture video yet. Well, maybe you have, but you don't have the green sheet. So that's why I'm kind of really ranting at length here. That is chapter 18, quiz number 2, our second quiz, again, which is also one of your homework problems that are due on Sunday. So double the benefit. All right, time for the read through. The specific heat of a substance varies with temperature according to some function. Find the energy required to raise this substance from 3 degrees Celsius to 13 degrees Celsius. So this is calculus now. There's not a ton of calculus in chapter. You won't see a lot of calculus until chapter 22, really. And we're starting out in chapter 18. So there's going to be a stretch where there's not much calculus, but this is an exception to that. This is I think a job. I think this is a job for calculus. And the only reason I'm saying that is because they're giving us a function. They're saying this is an engineered material. This material has a very precise, specific heat capacity value that's actually, that is a function. And so you would say, well, how do you do this? How do you have a substance that has a specific heat capacity that changes as a function of temperature? And the answer is chemical engineering and or material science. So this is a focus area for probably more than anyone, material sciences people, which the only reason I'm mentioning that's what my son does. My son works in Silicon Valley for a materials company, Stratasys. They're a 3D printer company. And anyway, I'll talk more about that later. But that's just is reminding me of, you do have highly engineered materials that have to exhibit certain characteristics. In this case, as the characteristics have to vary as a function of temperature. So I'm thinking of starting off with this. Well, I know Q equals MC delta T. I know that you would normally know that coming in today, but again, I know I'm repeating myself. You didn't really, I'm not assuming anyone hammered away on the lecture video, but this will be the only time I say that, because every Tuesday going forward, I'll say you guys for sure have digested, or the assumption is you've digested the lecture video. But for now, Q equals MC delta T. And you know what? I'm going to actually differentialize. So the differentialized version, differentialized. So this is sort of the, what I would call the, you could think of this as the macroscopic version. So I think of this is the macroscopic version of specific heat capacity. Here's the microscopic or differentialized version. It would be dq equals m, which is a constant, c, which is a constant, and delta t would become dt. So this is me going from the macroscopic expression for a specific heat capacity equation to the microscopic or differential. And differential means what's going on in the infinitesimally small realm from one little tick mark to the next tick mark. So this is my approach I'm thinking of for one reason only, because I was given the specific heat capacity as a function. Otherwise, I probably wouldn't be thinking of this. So with that said, find the energy required to raise the temperature of 3.1 grams of this substance from 3 to 13. So, all right, find the energy. So, energy needed to heat up. The energy needed to heat up this substance equals Q, that's the Q, and this is our dollar sign, that's what we're looking for. So now I just need to maybe integrate the left side and integrate the right side. So I'm going to end up with the integral from some initial amount of heat to some final amount of heat. So those are my boundary conditions of dq. That's my left side. Here's my right side. Integral from some initial temperature to some final temperature. These are definite integrals of MC delta T, MC dt. Okay, so I know I can bring M out of the integrand because that's a constant. Okay, and then I also know Q sub I equals 0. No heat. No heat flow at the beginning. No Q flow. No heat flow. No heat flow at T equals 0. Okay. So that just is basically saying there's no head start here. There's no heat flowing. You're starting from no heat flow to some final amount of heat flow, which is energy. All right, so number four, if I can solve that integral and evaluate it. So my left side now is going to become Q equals M times the integral, boundary conditions, of C, and C is 0.44 plus 0.49 T plus 0.034 T squared dt. So calculus. Another assumption here is you guys are all proficient with calculus in terms of just sort of basic derivatives and integration. We don't do anything really ever exotic in this course. On the other hand, you definitely know how to do this integration. So, and the assumption is you've had calculus. Anyone who has not had calculus should definitely not be taking this class. And I don't think that applies to anyone here, but Q equals M, and it's time to solve this integral. This would be 0.44 T plus 0.49. So power rule, T squared over 2 plus 0.034 T cubed over 3. And then I need to evaluate that from an initial temperature of 3 degrees Celsius to a final temperature of 13 degrees Celsius. Okay. And then that's it. So let's do this. We'll talk some more about this, but let's get a number. And again, you guys, at any moment, unmute your mic and just make a correction when you see me make a mistake, or ask a question or make a comment. Don't forget to convert from grams to kilograms. These are your green sheets, which look a lot like the lecture video. And here's the conversion factor we're going to need. 4.184 joules. Okay, 1 calorie is 4.184 joules. So I'm just going to write that down. 1 calorie is 4.184 joules. So here you go. All right. So let me see how people are doing. Let me just check the grade book here. All right. So we have an engineered substance that is basically its specific heat capacity depends on the temperature according to this function. Got it. Find the energy required to raise the temperature from 3 to 13 degrees. So this is a job for Q equals MC delta T because there's no phase changing going on. This is just a solid or a liquid that's warming up or cooling down. And then I went from the macroscopic version of Q equals MC delta T to the differential version. Okay, so then I integrated both sides. Yes, mass is a constant, so that can come out of the integrand. So I do have an expression that says Q equals M times the integral of C of the specific heat capacity function, which to me was 0.44 plus 0.49 T plus 0.034 T squared times delta T. Okay, so this C right here has now been replaced with its actual function. Good. Number 5, then I need to integrate. So if I integrate this function, Q equals M times 0.44 T plus 0.49 T squared over 2. So this is power function plus 0.034 T cubed over 3 evaluated from that low temperature to that high temperature. So how much heat was required to take this from 3 degrees to 13 degrees? So the answer is, and again, this is where you can shout out any questions or point out my mistakes when you see them. So this mass value is 0.0031 kilograms. And then I'll do it like this. This would be 0.44 T, and this is the final T. So this is times 13, 0.44 times 13, plus 0.49 over 2, and 0.49 divided by 2 is 0.245. So 0.245 T squared, so that would be 13 squared plus 0.034 divided by 3. I'll leave it as that because that's irrational. So this is 0.034 all over 3 times 13 cubed. All of this, whatever that is, minus 0.44 times 3 plus 0.245 times 3 squared plus 0.034 over 3 times 3 cubed. And that can be in its own parenthesis. Like that. Minus and then bracket. Okay. Let's try that. And then again, ask me questions and point out mistakes. If you see me make a mistake, it'd be great if you could let me know. 3. Okay, so this is going to be very similar to the problem I think we did to quiz 1. So I think I can pick up the pace. So we have another sample. This is interesting. We actually have a sample of liquid water and a sample of ice. So let's just start doing the read through. And the read through is critically important. I mean, and you guys hear me doing a lot of talking. And normally I don't, when I take an exam, I don't talk out loud. That would be pretty distracting. But I do have this internal conversation. You should get into that habit too. Just like have an internal conversation during the exam. And this is very much applicable to work. You're just sort of like verbalize or mentally having a conversation with yourself. This is liquid water. This is liquid water, and this liquid water is cooling. So we start off with liquid water that's cooling, and then this is ice. This is a solid known as ice, and it's ice warming. We have cooling liquid, cooling water, and warming ice, solid warming. Because apparently there's another energy device, there's another heat device, heat pump, that is transferring energy as heat from the liquid water to the ice. So we have that. So maybe as far as a diagram is concerned, I could say, well, here's my like isolated container. And in this container, I have basically water. Here's some water in my container. And then here's an ice cube that's also in this container. And I'm just reading this question very repetitively. A sample of liquid water. So I'm just going to write that down. So here's my sample of liquid water. This has a mass of 0.746 kg. Sample of liquid water and a sample of ice are placed in a thermally insulated container. That's what this black container is here. Thermally insulated container. The container also contains a device that transfers energy as heat from the liquid water to the ice. So here's how I'm going to represent that. Ready, set, go. Okay. This Q. So that is heat. That is heat being transferred, energy as heat from the liquid water to the ice at a constant rate P. So once again, there's that power term. I'm going to say power is the rate of energy flow. So I'm going to, and this equals constant. So this really does look familiar. Okay, until thermal equilibrium is reached. Okay, and thermal equilibrium this is thermal equilibrium right here at this point on the graph. That's thermal equilibrium. Okay, because they've both reached a constant temperature of 0 degrees Celsius at that moment in time. Okay, what is this rate? All right, so let's get started. So number one, P is power. It's the rate of heat removal. This is our dollar sign. Okay, so what do we do? What's Q? What's T? Where do we go? This is a job for reading the questions again. Specific heats of water and ice are 4190 and 2220 respectively, and with due utmost respect. Heat of fusion of an ice cube of ice is 333. All right. So there's nothing new here. I don't need to make any new introductions in terms of formulas or constants. So this is very much just and this is kind of what you could expect on the exam. I'm not going to give you this exact problem. I'm going to give you a variation of this problem. And this problem is very much a variation of the first problem. So it should be digestible. All right. So I know that the specific heat of water is 4190. I'm going to bark up that tree. All right. For Q over T, I'll use this. I'll use cooling water. And you could say, why are you going to look at cooling water? Why don't you look at warming ice? And the answer is I probably could. Maybe I can. But I'm going to start off looking at cooling water because that's what caught my eye. And I do know a lot about cooling water. And I think, just thinking out loud, I think I could take the same approach with warming ice, but I'm going to use cooling water. Number 3, let's keep going with that. What's Q? So during this cooling phase, this is the cooling phase. During this cooling phase of water, Q over T can be expressed as MC delta T over little t. And I better worry about subscripts. This subscript here is referring to the mass of the water. Oh, and that's why I chose water. You know what? Because if I do know the mass of the water, so that was actually just kind of a lucky guess. I do know the mass of the water. That's given to me. I don't know the mass of the ice. So it's the mass subscript W, which stands for water. It's C subscript W, which is the specific heat capacity of water. And it's the change in temperature for water. So let's get this answer. Ready? That equals mass of the water is 0.746 kilograms. Specific heat capacity of water per the problem statement is 4190 joules per kilogram Kelvin. That's MC delta T. Delta T is final minus initial. For the cooling phase, my water started out my water ended up at 0 degrees Celsius. And it started off at 66 degrees Celsius. And you know what? I'm actually going to write this. I'm not going to write that as Celsius degrees. That's incorrect. I'm going to write this as degree. No, let me back up. I'm not going to write this as degrees Celsius. That would be a mistake. I should write this as Celsius degrees because this is a difference. I am talking about a temperature difference. So this is a delta T. It's not T, it's delta T. So if I was talking about T, I might say, well, T is 31.3 degrees Celsius. But I'm talking about a temperature difference. So delta T, just making up numbers here, I guess would be negative 66 Celsius degrees. So there is a difference. I kind of made a big deal about this in the lecture video. Note the difference between degrees Celsius and Celsius degrees. And because that's a tripping point very often. So back to step number 3. Here's my numerator. Here's my denominator. MC delta T. How much time ticked off? And the answer is 1, 2, 3, 4 boxes. So it took 4 boxes to go from 66 degrees Celsius to 0 degrees Celsius. 4 boxes. Let's convert from boxes to time. This is scale. So for me, there are 80 minutes. T subscript S is given as 80 minutes for how many boxes? 1, 2, 3, 4, 5, 6, 7, 8. 8 boxes. And then I need to convert to seconds. So this would be 60 seconds all over 1 minute. So I'm kind of thinking, do we really need to be doing this problem? So maybe I'll be a little bit more selective going forward, because this is very similar. But maybe there's a twist. There's got to be a twist. There's got to be one or more twists, but just like there would be on an exam. So kilograms cancels with kilograms. Box cancels with box. Minutes. This is very noteworthy. Am I allowed to cancel? Can I cancel this? Can I cancel Celsius degrees with Kelvin? And the answer is yes, because of this earlier conversation. 1 degree Celsius does not equal 1 Kelvin. So this is no. 1 degree Celsius does not equal 1 Kelvin. However, 1 Celsius degree does equal 1 Kelvin. This is, I think, very helpful. This is hopefully you're finding it as exciting as I am, because this is a common tripping point. So I'm just going to highlight that for posterity. This will be very important to keep in mind. Okay, so let's get the answer to part A, unless I made a mistake. And if I made a mistake, we'll debug. But number 4, the power. And from a unit point of view, I am going to end up with joules per second. So that's good, because we all know that a joule per second is a watt. 1 watt is 1 joule per second. So I'm feeling good just because of the dimensions. 0.746 times 4190 times, and I'm going to ignore that negative sign, times 66 divided by 4 divided by store alpha A. P equals, I get 85.95 85.95785 joules per second, or watts. And again, ignore the negative. That negative is there. It's just, again, kind of a little commentary that says, hey, heat's being removed from the water. Okay, that's and let's do this. Store in calculator memory location A. SICM A. So store alpha A, because I'm pretty sure I'm going to need this number. But that's the answer to part A. What's the answer to part B? What's the initial mass of the ice in the container? So let's just keep going. Number 5. What's the initial mass of the ice in the container? So M subscript I. I stands for ice, is the $sign. That's what we're looking for here. So what to do? What's the initial mass of the ice? Let's do this. Let's do, here's the ice. This is the ice warming. So this phase is representing solid ice, remaining solid, but warming up. Even though it's warming up, it's still in the solid state right here. Okay. So this is a job for Q equals MC delta T. It's not, because I'm not going to, this segment right here, this is not going through a phase change. This is, again, this is ice warming up. Ice warming up. It's not going through a phase change. So that's just me saying Q equals MC delta T. And I better use some subscripts. This is M subscript I for ice, C subscript I for ice, and the temperature change for ice. So from that, I'm going to isolate mass of the ice, M subscript I, which stands for ice, is going to equal Q over CI delta TI. Okay, and I'm going to keep going. Then I'm going to kind of maybe just turn you guys loose. This is going to equal power times time all over the specific heat capacity of ice times the ice's change in temperature during that segment, during the ice warming up segment. Power is sitting there in memory location A. For me, how many boxes? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I have 6 boxes. So you know what to do with time. C subscript I, that's given. The specific heats of water and ice are given, 2220. And then delta T is going to be, I mean, for me, I end up at 0, but let's see, 0 to 66. Where did I start out at? Oh, I have to scale. All right, so this will be a little bit different too. 0 to some initial. So it's some final temperature. So this is some final temperature of the ice minus some initial temperature of the ice. The final temperature is right here. This is the final temperature of the ice. T final of the ice. This is the initial temperature of the ice. T subscript I is the initial temperature of the ice. So you're going to have to do the box thing again. So for here, there are 66 degrees Celsius corresponds to 1, 2, 3, 4, 4 boxes. Okay. So that's the conversion factor. So as far as ice is concerned, my ice started off at -3 boxes, 1, 2, 3. So if this is my conversion factor, I'll do it like this. I have 3 boxes times 66 degrees Celsius per 4 boxes equals what is 0.75 times 66, 49.5 Celsius degrees per box. Okay, so this is going to be 49.5 degrees Celsius. And it's negative because I'm going below 0. Ice is starting off at below freezing temperature. So it's really super cold ice. Okay, so this is my initial temperature of the ice is based on this calculation, -49.5 degrees Celsius. So I'll just write that here again. My ice is starting off at a very cold -49.5 degrees Celsius. So over here, let's see, and this is where I can maybe cut you loose a little bit. You know what P is? Power is sitting there in memory location A on your calculator. So that's what this is referring to. How much time did it take ice to go from -49.5 degrees Celsius to 0 degrees Celsius? It took 6 boxes. So you know how to deal with that. That's 6 boxes. You know the specific heat capacity of ice that's given to you. And we know the final temperature is 0 degrees Celsius. The initial temperature is negative 49.5 degrees Celsius. In my case, using my numbers. So you're going to have a minus. You're going to be subtracting a negative number. Okay, so let's all do that. Let's get the correct answer to part B. I think I said 6 boxes. It takes 6 boxes for my ice to warm up, not 8. Okay. Dimensional analysis. Sikkim A. This is joules per second. So from a dimensional analysis point of view, seconds cancels with seconds. So I'm going to have joules per seconds times seconds all over joules per kilogram Kelvin times Celsius degree. I know you're probably doing your own thing, but I'm just ranting away here in the background how I'm doing dimensional analysis, which is a requirement. And you want it to be a requirement. You want to do it. So seconds. Kelvin is the same as the Celsius degree. Okay. I do get kilograms that spit out. So yeah, good news. The dimensional analysis works out. And I'll talk more about dimensional analysis. So I have a feeling maybe not everyone is completely clear on what I'm doing here with the dimensions, but the dimensions do work out. They do spit out kilograms, and numerically I'm getting the right answer. So that's part B, which we're now officially done with. Understanding that there's still, some of you still might be working away. No worries about that. This is the answer to part B. So let me give that a special highlighter color. This was the answer to part A. Okay. Part C. What is the initial, when thermal equilibrium is reached, what is the mass of ice produced in this process? What is the mass of the ice produced in this process? All right, so number 7. Part C is asking for mass of new ice. We started off with 0.746 kilograms of ice, but that's not new ice, that's pre-existing ice. So we had a certain amount of ice that we started off with, but we actually produced some more ice in this process. And specifically, they want to know how much ice got produced during the period that I'll indicate right here. How much ice got produced during this period right here. It says when thermal equilibrium is reached, how much ice got produced in this process? And that's the answer right here. That much ice got produced because this is thermal equilibrium right there. Thermal equilibrium occurs right there. And so now we have to figure out, well, how much, what does this correspond to? This segment, this yellow segment is what happens when water is being phase changed to ice. Water is cooling. And during that process, I go from cooling water. So this is cooling liquid. Cooling liquid. This is phase changing liquid. So here I have a mixture of liquid and solid. And by the time that phase completes, I don't have any more liquid. I have pure solid, only solid by the time that equilibrium point is reached. Okay. So let's talk about how much ice got phase, or how much water got phase changed into ice. That's what this question is asking. So this is a job for Q equals M times L subscript F. So this is not new. We saw this before. We're seeing it again. So let's solve for, and specifically, I guess I should use subscript. So really, I should say Q equals mass of the ice, mass of the, this would be mass of the new ice, mass ice new times L subscript F. Okay, so having said that, algebraically rearrange it. The mass of the new ice that gets produced is going to equal Q all over L subscript F, the latent heat of fusion for water, which is a big deal because water is so fundamentally important in so many ways. But let's just I think we're kind of done here. So all you need to do is say, well, I know once again, for the umpteenth time, power is the rate of removing heat. And I already calculated that. That's in memory location A, courtesy of part A of this problem. So then I'm just going to say, well, again, Q is power times time, or memory location A times time. So that's what I'm going to put in here. This is power times time. Here's power times time. And we're looking at 2 boxes worth of time all over L subscript F. So let's get an answer on that. Let's worry about dimensional analysis and then be done with this problem. 2 boxes. 1, 2, 3. Okay. The number I get is, I get 0.30975 and some change, but I'm going to worry about dimensions. A is joules per second. T is going to be in seconds. The latent heat of fusion is given in terms of joules, although they use kilojoules, but we can convert joules per kilogram. So this yields, what does this yield? Joules cancels with joules, seconds with seconds. And once again, I have kilograms. So just repeating that, I do end up with kilograms. So my answer, this is the number on my answer, 0.3097 and some change kilograms. This is the answer to part C. Okay. A, B, and C. So we're done with A, B, and this is again part C. A, B, and C. Not a whole lot new, to be honest, but I guess chalk this up to reinforcement. So let me see how. Let me check the grade book. Okay. So there's, I think I need to allocate a bit more time. There's still quite a few people working away. So as you guys are finishing that up, again, feel free to ask questions. I'm going to get the next quiz ready. It's 10:04. I'm going to do this 5-minute break. I'll see you guys at 10:09. 10:09, we resume. 10:09. Ethyl alcohol is a boiling point. So we know a lot about boiling points. A lot. How much energy must be removed from a certain amount of ethyl alcohol that's a gas? So this is a drawing. So fight the good fight. Make a drawing. This is what you're going to have to use on an exam. So I'm thinking, why not get in the habit now of doing what you're just going to have to do on an exam anyway? And that includes, among other things, making a phase change diagram. In this case, ethyl alcohol is undergoing some temperature changes. How much energy must be removed from ethyl alcohol that is initially a gas? All right, so let's see. So here's like a nice phase change diagram. Let's kind of make a picture that looks like this. This is there. This is ethyl alcohol. So this is ethyl alcohol as a warming gas. Warming gas. That's what that arc portion is. Here's ethyl alcohol undergoing a phase change. Right? Let me make this a little bit more pronounced. Warming gas. So as I'm doing this, you should be doing this. This is, again, this is when you generate your reference material to prep for exam 1. Here's phase change. Okay. And then here's a warming liquid. All right, so this is a typical phase change diagram. Let's label this. This is warming liquid. Ethyl alcohol in the liquid state is warming up, warming liquid. And then, so we have, and then we start to phase change. So at this point, you reach the fusion point, the melting, the vaporization point of ethyl alcohol. So here we have a liquid and gas mixture, liquid plus gas. And then pretty soon, all of the liquid is vaporized into gas. And at this point, we just have, again, warming gas. I know I wrote that. Warming gas. Okay, so this is the phase diagram. And let me just make sure I'm clear on this. But in this case, we're actually cooling it. So technically, in terms of a direction arrow, we are starting out with ethyl alcohol at its boiling point. So right here, we don't have super hot ethyl alcohol vapor. We just have ethyl alcohol that's starting here at its boiling point. and then starts to cool. Okay, and I'm just reading this right here. This is saying how much energy must be removed from a certain amount of ethyl alcohol that is initially a gas at 78 degrees Celsius, 78 degrees Celsius, 78 degrees Celsius, which is the boiling point. So I am precisely starting right here at this purple dot. And then I'm cooling because I'm losing, energy is being removed. So I immediately go from gas to a mixture of liquid and gas. I continue to lose heat. And then at that point, I'm all liquid. And I'm going to have to adjust my graph here as well. So at this point, I'm going from a mixture of liquid and gas to pure liquid. And I can see I have to move this over. Let me get rid of this for a second. Okay, so I'm going from pure gas to a mixture of gas and liquid to pure liquid. My liquid is cooling down. And then I undergo a phase change from liquid to solid right there. There's my phase change. And I end up at the freezing point of ethyl alcohol per the question statement. All right, so here's my freezing. So a couple more labels. I'm going from gas to liquid and gas to just liquid to this would be a mix of liquid and solid. Liquid and solid. And at this point right here, I have pure solid. Only solid. Only solid at that point. And I need to change this word from warming to cooling. So, okay. Cooling. All right, so let's go through this again, because I think, to be honest, I think the calculation part isn't that strenuous. So I really want to kind of take advantage of the big picture items, which will help you when it comes to problem solving. All right, so just to play through this one more time, at least, I'm starting off, ethyl alcohol is starting as a gas at 78 degrees, which is right here, and then commences to cool. So as soon as it starts to cool, because it's right at the vaporization point, the boiling point, it immediately starts to go from pure gas to a mixture of liquid and gas. I continue to remove some heat. I'm left with pure liquid that cools during this phase. And then ultimately, all of the liquid, or ultimately the liquid cools to the freezing point of ethyl alcohol. And I have a mixture of liquid and solid. And by the time I'm done, right at this point, right here, I have only solid ethyl alcohol at its freezing point, negative 114. I didn't dip below negative 14. That would be a very interesting variation if you saw this on the exam. Everything's the same, except maybe it continues to cool, so it's actually a colder than freezing point sample of ethyl alcohol. But that's it. To me, this is helpful because it's wrapping my brain around the right. It's wrapping my brain the right way. So how much energy got removed? So we have a certain amount of energy that got removed here. We have a certain amount of energy that got removed here, and we have a certain amount of energy that got removed here. Maybe I can call this Q subscript A, that's segment A, Q subscript B, that's segment B, and Q subscript C for segment C. So let's just lay it out like that. So number one, the total amount of heat, Q, is just going to equal QA plus QB plus QC. Number 2, what's QA? Let's look at QA. QA is referring to phase change. So this is going to be a job for phase change. M, L subscript, V for vaporization. So notes, this is for A, this is gas converting to liquid. Gas is converting to liquid. That is a phase change. So let's get a number on that. The amount of heat that must be removed is going to equal point something. 0.784 kilograms times the latent heat of vaporization of ethyl alcohol, which is given 879,000 joules. So it says kilojoules. Here's how I'm going to write down kilojoules, just because this is a common way to represent an exponent. 879 E3 joules per kilogram. So let me just a word about that. 879 kJ equals 879,000 joules, or I would just typically write that as 879,000 joules, or again, I would write that as 879 E3, which is the same as saying 879 times 10 to the third. So it's just a shorthand notation. All right, so we got an answer. Let's get an answer. You can see kilograms cancels with kilograms. So let's do that. And store it in calculator memory. 0.784 times 879 is some number. Store alpha A times 1,000. Store alpha A, 689,000. 689,136 joules. And let me just do a discount double check. Point. What is the mass? 0.784. 0.784 times 879 E3. I guess that's it. Okay. So let's do B. On to segment B. Segment B is, again, Q sub B. This is corresponding to cooling liquid. So cooling liquid, we have Q sub, this is a job for MC delta T. MC delta T. MC delta T is what you use for a liquid or a solid heating up or cooling down versus a phase change. So let's just go with this. M is still that 0.784 kilograms of ethyl alcohol. See, the specific heat capacity of ethyl alcohol is given to us. Let me start erasing this. We know the freezing point. We know the heat of fusion, L subscript V. There it is, specific heat capacity. So the specific heat capacity is 2.43, but that's given as kilojoules. So I'm just going to say the specific heat capacity is 2430 joules per kilogram Kelvin. MC delta T. Delta T now, what's this temperature? This temperature is the boiling point. This is 78 degrees Celsius. This is the freezing point. The freezing point is given as negative 114 degrees Celsius. So I'm going to end up at my final temperature is negative 114 degrees Celsius minus the initial, and the initial was 78 degrees Celsius. But now watch what I'm doing. I'm not going to write down degrees Celsius because this is a temperature difference. So instead of degrees Celsius, I'm going to write down Celsius degrees because once again, this is a temperature difference. So this is a delta T. That's why I'm using Celsius degrees. And I guess that's it. Cancellation. I'm going to have kilograms cancels with kilograms. And once again, this is I really want to stress this. This Kelvin degree here is the same as a Celsius degree here. So those are equivalent. So I can cancel those out. So I am left with joules. Numerically, what do I have? 0.784 times 2430 times, and I'm going to ignore the negative sign, negative 114 minus 78. Okay, that's a lot of heat getting removed. I actually have negative 365,783.04 joules. But I'm actually going to record this as 365,783.04 because this negative sign, this is just a reminder that energy is being removed. Reminder that Q is removed from sample. So this is going to be my answer for Q subscript B. This is my answer for Q subscript A. This is the heat removed during segment A. This is the heat removed during segment B. I'm going to definitely stick this into SICM B, SICM, calculator memory location B, just like this was SICM, calculator memory location A. So store alpha B. Let me update that. Store alpha B. Okay. Last but not least, the final phase change. So now I'm looking at Q subscript C, number 5. Q subscript C. This is referring to the phase change. This is the phase change from liquid to solid, phase change from liquid to solid. And there is a special term for this. This is called fusion. Fusion is the name of the phase change from liquid to solid or from solid to liquid. It actually is used for both of those. Okay, so let's do this. Q subscript C. This is a phase change. It's not cooling or warming up. This is a job for M. L subscript F, not L subscript V. Up here, I used L subscript V because I was going from gas to liquid. Here I'm using L subscript F because I'm going from liquid to solid. So that's why L subscript F. Mass is going to be 0.784 kilograms times the latent heat of fusion for ethyl alcohol is given as 109,000. So this would be 109 kilojoules, which I'm just going to represent as E3, 109,000 109,000 joules per kilogram times, I guess that's it. That is it, times nothing. All right, so let's get a number on that. 0.784 Okay, times 109. This is 85,456 joules. And this is Q subscript C. And let's put that in calculator memory location C. So now step 7, store alpha C. Step 7, the total amount of heat that needed to be removed from this ethyl alcohol, starting off in a gaseous state, is QA plus QB plus QC equals calculator memory location A plus calculator memory location B plus calculator memory location C, or 114, nope, 1,140,375.04 joules. That's the answer. Phase change diagram. Okay. I mean, to me, the real value of this is just spending that giant amount of time constructing this, because I think this is very insightful. This gives you a lot of understanding, and the rest of it was pretty operational. All right, so onward to quiz 5, but this is quiz 5, 18.48.
Professor, will you be posting this lecture anywhere?
Yeah, this I'll post the link. I'll put the link in our homepage, because for sure you guys should all be like reviewing this lecture. But yep, definitely. Okay, so let me get a snap. Yep, sure. Here's 1848. Looks so easy. This won't take time as far as calculations are concerned, but I can certainly say a lot about it because this is a brand new topic within chapter 18. Okay, so this is chapter 18, quiz 5. So up until now, we've talked about the following. We've talked about warming. We've talked about solids and liquids warming up or cooling down. So when you look at a solid or a liquid warming up or cooling down, that was a job for Q equals MC delta T. Then we spent a lot of time talking about phase changes. Phase changes was the other major component that we've covered so far. And phase changes could be from between the liquid state and solid state, or between the solid state and gaseous state, or between the liquid state and the gaseous state. And again, I talk a lot about this in the lecture video, the green sheet lecture video. But this last one, from liquid to gas or gas to liquid, that's called sublimation. And you see an example of sublimation. If you've ever left an ice tray in your freezer for a long time, like after a few weeks, you look at the ice and it looks like it's kind of wilted or shrank. It looks like it shrank a bit. And that's because liquid will basically go directly to the gas state. You lose the liquid, or let me hang on. Liquid to solid. This is sublimation. This is what I'm talking about. Sublimation. So when an ice cube loses some liquid because it's being converted to gas, that's why That's why the ice cube looks like it shrank. Solid to gas. This is fusion. This is the fusion process, and liquid to gas or gas to liquid, that's vaporization. Okay, so anyway, that's what we've talked about thus far. That's a big part of chapter 18. It's tomorrow. It's Thursday's lab. So now we kind of switch. We're gonna switch, or we're going to progress. Now we're going to talk about the first law. First law of thermodynamics, which is a very cornerstone type of concept. First law of thermodynamics is what the remainder of chapter 18 is, and this definitely bleeds through to chapter 19 and chapter 20. Thermodynamics is a big deal. If I just go to my lecture notes, and then you will have these on Thursday, but you have access to them now basically via the lecture video. And this is the section we're getting into right here, right there. A closer look at heat and work. Time to derive the work done by a gas. So this is these will be completed for you via the lecture video. So you're going to watch the lecture video, and the lecture video will reveal all of the stuff that you see here. So when you write it down on your green sheets, you're going to be getting it from the lecture video, getting the content, getting the stuff that you fill in these blanks with from the lecture video. And again, the thinking is you're going to hopefully, you're not going to quickly copy it down. You're going to think through it as you copy it down. Okay, so and then this sort of culminates in the first law of thermodynamics there. This is the first law of thermodynamics right here. Okay, so I make a very big deal about this in the lecture video because it's, again, a very cornerstone concept. It's how you keep track of nature. First law of thermodynamics. It basically is allowing you to keep track of energy, and energy in three different forms. Energy in the form of internal energy, heat energy, and work. These are all versions of energy. So that's what awaits you via the green sheet lectures and the green sheet transcription process. And I'm going to talk a lot more about this on Wednesday, but I'll introduce it now, I guess, as good a time as any. Although the better time would be after you watch the lecture video. So let me state that. So here we go. You have, this is chapter 18, quiz 5. Gas within an enclosed chamber passes through the cycle as shown. All right, so here it goes. This is brand new introductory stuff. So I'm going to use a balloon as a metaphor. All right, so I'm going to think of just a balloon like this. Let me use a red balloon. Here's a red balloon. Not good. Good enough. Here's a red balloon. This is a red balloon. So I'm gonna basically use a red balloon as my metaphor for what's going through the system. This balloon is my system. So gas within a chamber passes through the cycle as shown. So imagine a balloon, and this balloon is filled with a gas like air or helium or whatever, nitrogen. But this balloon is filled with a gas, and we refer to, in this case, we're going to refer to the gas as the working substance. I just want to get that term out now. Working substance. Working substance is the substance that's actually doing the work or getting worked on. Working substance in this case is a gas because it's stated as being a gas. So imagine a red balloon with some gas in it, and it passes through this cycle that you see here on this graph. All right, so now let's talk about this cycle. This cycle right here, this is pressure versus volume. And this graph here is referred to as a PV diagram. A PV diagram is a graph where you have pressure on the y-axis and volume on the x-axis, PV diagram. That's what, and you're going to hear this term hundreds of more times in this class. PV diagram, that's what we're looking at here. Okay, so from thermodynamic state A, I'm starting, this red balloon is starting out at thermodynamic state A, and then going to thermodynamic state B. And it's going straight up, as you can see here. All right, so for this, I'm going to say this is a constant volume process. You can see that some stuff is changing. Pressure is changing, but volume stays the same. So this is constant volume process. It's a vertical line. So notice whatever the volume value is right here, so V at A, which is the same as V at B. The volume of this balloon at thermodynamic state A is the same as the balloon's volume at thermodynamic state B. It hasn't changed in size, so hence the term constant volume. And there's a special term for that. This is called an isochoric. So from A to B, this balloon undergoes an isochoric process, isochoric. Constant volume means isochoric. Isochoric means constant volume. So how the heck, how can I increase the pressure? Because the pressure of this balloon is increasing. How can I increase the pressure of this balloon while maintaining a constant volume? One way that I'm kind of thinking of, I'm going to put this balloon in a box. So if I put this balloon in a wooden box, for example, then I might have something like this. So let me just update that a bit. I'm going to very tightly encase the balloon in this box. So this balloon is constrained. It can't expand. And you could say, well, yeah, Chris, it could still expand into this region right here. But let's just say this balloon, the balloon's volume is not allowed to change. It's not allowed. It's just stuck in a box. So if this balloon was not able to expand, and the other way I could think of, like, what if you like coated it with some solid coating? Like, what if you painted it with really thick paint? The balloon is just sitting there, but it's painted and it won't be able to expand or contract, actually. So how can you increase the balloon's pressure while maintaining its volume, which is again happening during this state right here? Okay. And the answer is add heat. So I'm going to dump some heat into the balloon. Ready, set, what's good for heat? Heat. All right, so there. If you add heat to and you guys notice, this is like a common sense thing. If I add heat to this balloon and the balloon can't expand, the pressure is going to go up. I mean, you know what? This would have been better. It would have been better to use a bicycle inner tube, a bicycle tire inner tube. If you pump air into your bicycle tire, its volume pretty much stays the same, but its pressure increases. That's why you pump air into your bicycle tire. That probably would have been the better example, but we're good, hopefully. Bicycle tire is a great example. All right. So if I add heat to this balloon and it can't change its volume, its pressure is going to go up, just like, again, a bicycle tire. All right, then from B to C, from thermodynamic state B to C, what's happening? Determine the energy added to heat to the system as heat during process CA if energy is added as heat during AB. So yeah, they're saying for sure there's some heat. So I'm going to label this QAB. This is you adding heat to your bicycle tire. I'm just going to switch to that. You're adding heat to your bicycle tire. Your bicycle tire doesn't change size. It just increases in pressure while maintaining a constant volume. And then I'm just going to read the question again. If the energy added as heat QAB during process AB is 20 joules, no energy is transferred as heat during the process BC. So from BC, let's look at process BC here. BC, there's thermostate B, there's thermostate C. No energy is transferred as heat from B to C. So you know what? That actually has a special name. So no energy is transferred from B to C. So Q equals 0. And there's a special name. This is called an adiabatic. Adiabatic means a thermodynamic process where there is no change in heat. Adiabatic. Adiabatic. So this is, and in fact, this is adiabatic expansion. Because notice that the balloon, I guess I'm going back to the balloon is actually increasing in volume expansion because I'm going from a pretty low volume at state A. So state A is right here, pretty low volume. State B, state C, I should say, much higher volume. Adiabatic expansion. Okay, good to know. And the net work done during the cycle is 15 joules. Okay. Use a minus sign to indicate energy decrease. All right. So we've talked about energy state A to B a lot, from B to C. Now let's talk about C to A. C to A. This is a constant, so I'll just say from C to A, this is a constant pressure. So notice on this graph, the pressure is not changing. The volume is decreasing, but the pressure remains the same. So this is a constant pressure process. And this has, there's I think 6 special names, really 5 special names that you're going to have to get familiar with in this chapter. And you will. Constant pressure means isobaric. So this is an isobaric contraction. The volume's getting smaller. So I'm saying contraction because the balloon is shrinking. Isobaric means it's shrinking at a constant pressure. Okay. And that makes sense. I mean, if you just have a balloon, if you're holding a balloon in front of you, and you cool the balloon is, as the balloon's cooling, the temperature is going to decrease, but the pressure remains the same because it's just sitting there in the ambient pressure environment. So sitting there in the same atmospheric pressure environment that you're sitting in. All right. So those are the 3 processes. Okay. So let's do this now. Here's a great way to keep track of things. This is called a thermo table. And this is spelled out in it's not really spelled out, but it's referenced in the green sheets. And it's just a way to keep track of things. So you guys were all engineers and scientists here. We all like to think rationally and logically. We all like structure and standards and at the same time being creative and dreaming up new stuff. But here's a thermo table. I'm gonna create a thermo table based on the first law. Change in internal energy equals Q minus W. This is, once again, this is the first law of thermodynamics. Change in internal energy equals Q minus W. So if you're going to interpret this, you would basically read through this as this is the amount of gas energy. Amount of gas energy. So you guys know little gas particles are flying around like crazy. So if you look inside this balloon, here's a gas molecule right here. So let's look at a gas molecule inside this balloon. There's one of many gas molecules. And this gas molecule inside the balloon is flying around like crazy. And it possesses kinetic energy. It possesses it possesses kinetic energy. I'll just write that as K. And this right here, what I'm indicating here, this is the internal energy. So whatever the kinetic energy is of that gas particle, we refer to that as internal energy, a very special term. Internal energy of that gas particle, and then we would add all of the gas particle energies together to get the total internal energy. And there's a special, it's E for energy, INT for internal. Okay, so that's it. Let's do this thermo table approach now. This is just segmenting things into bite-sized pieces. All right, so I'm going from thermostate A to thermostate B. And I actually did refer to that as isochoric. So let's give that a name. Isochoric. Isochoric is the name of the process from A to B because the volume remains the same. And then I'm going from state B to state C, right here. Here's state B. Here's state C. And that was referred to adiabatic. Adiabatic, no heat flows in or flows out. And this automotive engines include an adiabatic step. This is adiabatic expansion. That's B to C. And last but not least, C to A. This is known as isobaric contraction. And if you're wondering, I'm going to get completely lost by all this terminology, you won't. There's a certain amount of terminology that you have to get comfortable with. But in the big picture, you guys, there's not a huge amount of terminology, but there's some. All right. And so then I go from state A to B, from B to C, and then from C to A to B, B to C, C to A. And then, so I'm just going to add these all up. My complete state is from state A to state B to state C, back to state A. So I kind of just make a little table out of this. So let's convert this into a table. So let's just grid this up. All right. So nice and logical, nice and tabulated. And I got to move some stuff around. So let's spend a chunk of time making a nice, neat table. This effort is very much worth it. And you'll see why. Maybe you can see why now. Look how nice and logical this seems to be. All right, so I'm just going to move a little bit of housekeeping here. That looks good. Oh, not quite. Okay. So now let's fill in this table to the maximum extent possible. And all of this is going to be great. This is all great background. All right. What's the change in internal energy from A to B? I don't know. Well, let me read it. Gas within the chamber passes through the cycle as shown in the figure. Determine the energy added to the system as heat during CA. So there's my dollar sign. So let's put the dollar sign where it belongs. Determine the energy added to the system as heat during process CA. So that's down here. Here's CA. And you know what? I'm actually thinking I'm going to go with my instincts. The only way this balloon can maintain a given pressure and yet shrink, the only way that can happen is if heat energy is removed. So I'm going to draw it like that. This is QCA. QCA is the amount of heat that must be leaving the balloon, which explains why the balloon does get smaller, but it's getting smaller at a constant pressure because it's just sitting there in the ambient atmosphere. And we said QAB was going in here. So that's the dollar sign. Determine the energy added to the system as heat during process CA. Here's CA. Right here is my dollar sign. Cha-ching. That's the dollar sign. This is the energy added to the system during process CA. All right, now let's talk about process AB. Process AB, I don't know anything about the internal energy. I don't know anything about the heat that's flowing in. All I know is the heat's flowing into the system, but I do know that work is zero. So I can write zero. And then just a little, I need to explain that. For process AB, no work occurs. No work occurs because there's no movement. And you guys should know from your prior physics class that work is force times displacement. And if there's no displacement, there's no work done. So the forces acting on the balloon, the forces are not equal to zero, but the displacement is equal to zero because you're preventing the system from moving. Displacement is equal to zero, which means that the work is zero. If nothing moves, work equals zero. So that's what I'm saying. Work is zero for process A to B. From B to C, how much internal energy? I don't know I don't know numerically what's happening with internal energy, but I do know that there's no heat exchanged. And then this is a question mark. And then last but not least, this is a contraction, isobaric contraction. So I'm going to leave that right here from now. Okay. So I'm going to read this question again. If energy is added as heat from A to B, got it. If the energy added from A to B is 20 joules. So I'm going to replace this dollar sign with 20 right here. So, because I do know it's saying if the energy added from process A to B, energy added as heat from process A to B is 20. So I'm going to change that from a question mark to 20. No energy is transferred as heat from B to C. So I've accounted for that. This is what that's referring to. No energy is transferred as heat in or out from B to C. That's adiabatic. That's my adiabatic expansion. And the net work done during the cycle is 15 joules. So the net amount of work for the entire cycle is 15 joules. And that goes here, 15 joules. And why do we have heat engines? Why do people like heat engines? Because engines do work for us. So in the case of a heat engine, we're going to actually tap into heat and have heat do work for us. All right, so I can do a few things here. I'm going to kind of wrap this up. All right, so I know, let's see, if internal energy is Q minus W, and I know Q and I know W, so you know what? I can now replace this. What's 20 minus 0? The answer is 20. Got it. Okay, I also know the following. From A to B to C to A, for this entire process, this entire thermodynamic process, if I make a complete round trip, so if I'm starting at A and I'm going to B, from B to C, so from C to A, I'm right back where I started from. So overall, the net effect is, the net change in internal energy is 0. So for that entire closed loop, I can write this as 0. Okay, so that is 0. This is 15. So I'm feeling pretty good here. This is, let me highlight. This is 0. This is 15. And we're looking for the amount of heat that flowed out of the system from C to A. So once again, this is what we're after. This is our dollar sign, QCA, right here. So let's see. So whatever this is, whatever this value, so 20 plus that value equals 0. So I'm going to add up the columns now. Similarly, 20 plus 0 plus dollar sign equals this. Let's just write that as 20 plus 0 plus dollar sign is 20 plus dollar sign. Okay, so once again, what is 20 plus 0 plus dollar sign? It's 20 plus dollar sign. And then over here, last column, 0 plus whatever this is, plus whatever this is, equals 15 joules. Okay, so that's it. And again, I don't know this dollar sign, I don't know this dollar sign, but I do know that whatever 0 plus this is, it's 15 joules, and then we're done. So then all you do, we're going to look at this net result. The net result is 0 equals 20 plus dollar sign plus 15. So just treat it like algebra. 0 equals 20 plus dollar sign plus 15 joules. And this should be joules. So you know what? Dollar sign equals -5, right? 0 equals, yeah. So 20 joules plus 15 joules, 35.5. Use a minus sign. No, let me check something. The net work done during the cycle is 15 joules. And then 20 is 20 joules plus dollar sign. Okay. And this should be a plus. Okay. I need to check my housekeeping here for a minute. The net work done during the cycle is 15 joules. The energy added is heat QAB is 20, and that's energy in. No energy is transferred from B to C. And the net work done, okay. Determine the energy added to the system as heat during CA. Okay, that's good. I got that. All right, so from C to A, dollar sign is -5. Okay, just had to double check. Okay. Because I needed to change this. Sorry. Let me just tighten this up. So 20 equals 20 minus 0. Dollar sign equals 0 minus dollar sign. Dollar sign here equals dollar sign minus question mark. So here, 0, right here, 0 equals 20 plus dollar sign minus. So let me just clean that up. Okay, so I have 0 equals 20 plus dollar sign minus 5. Minus 15. Okay. There. Okay. So this is all brand new. It would make a lot more sense if you saw the video first, because I go into even more basic introductions, but that's it. It is now 11:11. This is chapter 18.